Welcome to Mana Studies. Let's continue where we left in the previous video. We were focusing at some graphs. Now we are going to focus at the graph of y equals to 1 upon x square or 1 upon x to the power 4 or 1 upon x to the power 6. That is when the power is an even multiple. As it can be seen that the power can be written as twice of m, where m is a positive integer. So the graph would look like this. Till now, we have covered that the graph y equals to x square was created by putting in the values at x and then calculating the value of y, and that is what we are doing till now. But this will be explained later in the part of the chapter, that is graph sketching. But till then, let's just assume that this is going to be the graph, and for better understanding, it can be assumed that if you put positive value of x or negative value of x, in either way, the value of y is going to be the same. If x is equal to plus 1, then also y is equal to 1. If the value of x is minus 1, still the value of y comes out to be 1. In this case, when you're drawing the graph of y equals to 1 upon x cube or 1 upon x to the power 5, that is the power is an odd multiple, then the graph would look like this. As if you input plus 2, then the value would be 1 upon 8, and if you input minus 2, then the value would be minus 1 upon 8. Now let's look at the third one, that is when the power is y equals to 1 upon x to the power minus 1 by 2. So it will go in the denominator, and there will be a radical sign because the power is written as 1 upon 2 with a minus sign. This minus brings it into the denominator and 1 by 2 brings in the radical sign. या फिर ऐसा हो सकता है कि ये that is x to the power 1 by 4. The graph of this one would look like this, because inside the under root we cannot put negative value, so the graph will not exist in this region, and because output is also always positive, therefore the graph will not be in this region. Therefore it is better to remember that the graph of y equals to 1 upon root x looks like this. Let's move forward to the last one, that is the graph of y equals to 1 upon cube root of x or 1 upon x to the power 1 by 5. This minus brings the term to the denominator, and the power 1 upon 5 brings in the radical sign. Now the graph would look like this, which, as you may remember, is quite similar to this one. These two graphs look similar, though the values are not same, but the overall shape remains the same. Now let's focus at the exponential graph, exponential function, or the graph of the exponential function. Let's say y equals to a to the power x. If it is given, then this a belongs from 0 to 1, then we are going to draw the graph over here. And if the value of a is greater than 1, then we are going to draw the graph over here. If the base is greater than 1, now if you keep on increasing the value of the exponent, that is the power, when base is greater than 1, and if the value of exponent is continuously increased, then the value of function will also increase exponentially. So this is known as the exponential graph. Whereas if the value of base is less than 1 but greater than 0, then as you increase the power, the term will decrease in its value, so the graph would look like this. Now let's focus at the logarithmic function. In the logarithmic function, again we will assume that y is equal to log a x, where a is the base. If a is greater than 1, then the logarithmic function would look like this. Now if x is equal to 1, then this would look like y is equal to log a 1. What should be the power of a so that the outcome is 1? The power should be 0. Therefore we can say that at 1 the value of y will be 0. So that is the root of the equation, or the x-intercept. Now if the value of a ranges between 0 and 1, then the graph would look like this. Now let's calculate when will y be 0. Then a to the power 0 is equal to 1. So similarly this point will be 1, 0. It's better to remember these graphs, and the elaborate discussion on how these graphs are sketched would be in graph sketching, that is application of derivatives. Let's move forward to the signum function. Now signum function is another interesting concept. In signum function, if any value of x is input that is a positive integer or a positive real number, that is 1, 1.1, 2, 2.2, 3, 3.5 or any number, then the output of signum function will remain a 1. Whereas if the input in the signum function is any negative value of x, any negative real value of x, that is minus 1, minus 2 by 3, minus 10, then the output would be minus 1. And the special case is if you input 0 inside this, then the output is 0. So signum function can be written as signum function of x is equal to, there are only three outcomes, plus 1, minus 1 or 0. When will we get plus 1? When the value of x is greater than 0. When will we get minus 1? When the value of x is less than 0. And when will I get 0? When the value of x is equal to 0. And the point to be remembered is x belongs to the set of real numbers. Now let's move forward. Now we have trigonometric functions. To remember them, the graph of the function sin x is a periodic one and it looks like this. Now we are going to focus at the terms which we discussed in the first part of this, that is domain of the function, range of the function, period of the function, asymptotes if exist. So let's start looking. This is 0 and if I input 0 in place of x, then the value of y is also 0. And when will the value of y be 1? When the input is pi by 2. And when will the value be 0? When the input is pi. Similarly, this point would be 3 pi by 2 and this will be 2 pi. As it can be seen that the graph repeats itself after an interval of 2 pi. This we covered in the previous part. So the period is 2 pi. Now domain of the function. Domain is the set of values that can be input into sine. The set would comprise of all the real values, the set of real numbers. Now the range, as we can see that the lowest possible value of this graph goes till minus 1 at sine 3 pi by 2 and it will be repeated at an interval of 2 pi, and the maximum value goes till 1. So the range of the function would vary between minus 1 and 1. And let's look at asymptotes. The definition of asymptote is a line towards which the graph tries to move indefinitely but never touch, and there is no such line in this case, so it will be not applicable in the case of sine. Now let's look at the another graph which will be of cos x. So if we have to draw the graph of y equals cos x, then the graph would look like this. This point is 0 and when we input 0 in place of x, the output is 1. When we input pi by 2, then the output is 0. At pi the output is minus 1 and at this is going to be 3 pi by 2, and at 2 pi, that is when the graph returns back to 0. This is 0 and when you return back to 0, that is 2 pi. Still the value becomes the same thing, that is 1. So we can say that the domain of the function is the set of all real numbers. Then because all the values of x can be input into this one as we move forward or backwards, then the range of the function would comprise of all the values between minus 1 and 1. So we can say that the domain and range of both sine and cos are exactly the same. Then the period of the function can be observed that the graph repeats itself after an interval of 2 pi. So the period is also same for sine and cos. And as we can see in this case, there is no line towards which the graph is approaching indefinitely. So the case of asymptotes is not applicable for cos as well. Now let's look at the graph of tan. Now the basic confusion at this point is people have a confusion about the value of tan 90. If you are confused about tan 90, let's look at an example. Let's say this is a circle of radius r and This line would also be of length r. Let's assume this is an angle theta. The coordinates of this point are a comma b. That means the distance on the x-axis is going to be a and the distance on the y-axis is going to be b. If the angle approaches 90, I would like write it as tan theta. When theta is approaching the value of 90 degrees or pi by 2 radians, then as we can see, tan is the ratio of perpendicular upon base. When this angle approaches 90, that means this side would approach the length r. It will approach the length r divided by base. Since base is approaching 0, this will be a very large number. And as we all know that infinity is not a number, infinity is a notion. Therefore, we can say that when theta approaches 90, tan approaches a very large number. So when tan will be calculated at 90 degrees, the value is called undefined, because the value of tan 90 is not defined in any case. Now we are going to draw the graph of tan, and the graph would look like this. The y-axis, the x-axis, 0, this is pi by 2, pi, and minus pi by 2. Let me just draw some reference lines so that I can see clearly. At pi by 2 it approaches infinity, at 0 it is 0, at negative pi by 2 it will approach negative infinity, and similarly this graph will be repeated on the other ends as well. As you can see that the graph repeats itself after an interval of pi. So the period in this case for tan, the period will be pi range, that is the values of the values on the y-axis which will be obtained are approaching positive infinity, approaching negative infinity. So we can see that range would comprise of all the values in the set of real numbers. Now the tricky part is the domain. While calculating the domain, that is the possible values of x which we can input, we have to exclude pi by 2. We can include pi, but we again have to exclude 3 pi by 2. As you can observe in these two numbers, that we have to exclude an odd multiple of pi by 2. And how to write this thing? An odd multiple of pi by 2 would be excluded. That is to say, 2m plus 1 into pi by 2 has to be excluded from the set of real numbers. This becomes the domain of the function, that is all real values except odd multiples of pi by 2, since at these values the graph of tan is not defined. Let's move forward. But before that, I would like to clarify the point why tan 90 was undefined. Let's take another example. This is a number line, that is a visual representation of all the numbers. Let's say there is a number 0. I should move this upwards in order to get some space for calculations. So now this is going to be the number line, the visual representation. If this is a point 0 and I'm going to approach 0 from right hand side, that is from the positive side. If I'm approaching 0, that means I have to calculate the value of 1 upon 0. And if I'm approaching 0 from right hand side, the first number I stop at is 1. So 1 divided by 1 is going to be 1. Let's say I move a bit closer and another number is 0.1. So now I'm going to divide 1 by 0.1. The output will be 10. Now I'm going to take a step closer. Another number closer to 0 will be 0.01. So now I'm going to divide 1 by 0.01 and the result would be 100. Now as you can see, this number is constantly increasing. So the more closer I step to 0, this number moves towards a very large number. And the very large number, this concept is denoted by the symbol infinity. Now let's look at from the other side. If I'm approaching 0 from left hand side, this means I'm going to move from minus 1. 1 divided by minus 1 is equal to minus 1. Let's take a step towards 0. It will be minus 0.1. Now if I divide 1 by minus 0.1, this would look like, this would be minus 10. Let's take another step forward. It will be minus 0.01. By doing this, I'm moving closer to 0. So now the denominator will be minus 0.01. So the result will be minus 100. As we can see, the magnitude is increasing, but because there is a negative sign, that means the number is decreasing. So let's just focus at the magnitude and the sign separately. I say there is a negative sign, and in front of the negative sign, this number is tending towards a very large number. Now the concept of very large number is denoted by the notion infinity. So it will be written as minus infinity. Now if 1 is divided by 0 and I approach 0 from left hand side, then it's a negative large number. Magnitude is large number. And if I approach 0 from right hand side, then that is another large number, but this time with a positive sign. So because we cannot clearly say whether it's going to be negative or positive, therefore 1 upon 0 is called undefined. 1 upon 0 is not infinity, it is undefined. 1 upon 0 can either be positive or negative, therefore it is called undefined. It is not equal to infinity. Let's move forward on the topic we were discussing. That is the graph of y equals to cot x. Now I'll again draw some reference lines. The graph of cot looks like this, and as you can observe that the period is pi, since the graph repeats itself after an interval of pi. Let's talk about domain. Now what is the domain? Now domain is again the tricky part. While inputting the values of x, I cannot input either 0 or pi or minus pi. So it is all the multiples of pi have to be excluded. So it will be the set of real numbers excluding multiples of pi, where m belongs to integers. Either it could be 0 or it could be 1, so that will become pi, or it could be minus 1, so it will become minus pi. All these terms have to be excluded from the domain. Let's look at range of the function, and as we can see, the range extends, approaches positive infinity and also approaches negative infinity. So the range of the function is the set of all real values. Now the two interesting graphs, which are sec x and cosec x. If I'm focusing at sec x, so there is a trick to remember this graph, since we all know that sec is the reciprocal of cos. So it's better to visualize the graph of cos first and then to symmetrically draw the graph of sec. This dotted line is the graph of cos, and by using it we are going to remember how the graph of sec should look like. This line represents plus 1, this represents minus 1. So now the graph of y equals to sec x would look like this. Since at this point, which is pi by 2, the value of cos would be 0. And as we know that sec x is equal to 1 upon cos x. So the denominator should not be 0. Cos x should not be 0 for the function to be defined. So if cos x becomes 0, at that point sec x will not be defined. Therefore, at pi by 2 cos is 0, so the graph of sec x is not defined. Similarly, on the negative side, that is minus pi by 2, and on the positive side, as we can see, this is going to be pi by 2. Here we will have pi, here it will be 3 pi by 2, and this point will be pi. So the graph would be this, then this, and not defined at pi by 2 and 3 pi by 2, not defined at 3 pi by 2 and 5 pi by 2. So the bold or the highlighted curve is the graph of sec x, and the dotted one is the graph of cos x. The domain of the function, that is all the values which can be input, the values of x which are acceptable, will include all real values except odd multiples of pi by 2. That is the values at which cos becomes 0. So domain will be all real values except odd multiples of pi by 2. Let's look at range of the function. Range will include all values above 1 and below minus 1. That means all real values except no, all real values except the interval between minus 1 and 1. It will be open interval because minus 1 and 1 are included. At 0, when you input 0, cos 0 will be 1 and the value of sec 0 will also be 1. So 1 is included in the range, whereas the numbers till 1 are not included. And the period of the function would be same as cos because the graph repeats itself after an interval of 2 pi. So the period is 2 pi. Let's look at the next graph, that is going to be of cosec x. So the graph of cosec x is a bit symmetric to the sine one, so it's better to draw the graph of sine first in order to memorize easily the graph of cosec x. First, let's draw some reference lines so that we know where we are sketching it. Okay. Mm, This is the line where y is equal to plus 1, and this is the line where y equals minus 1. So now the graph, as we saw in cos sec x graph, we can write that cosec x is equal to 1 upon sine x. For the graph to be defined, sine x should not be 0. If sine x becomes 0, 1 upon 0 is not defined. So sine becomes 0 at 0 and at pi. So the graph of cosec x is not going to be defined at these 2 points. And when sin x becomes 1, that is at pi by 2, that is when cosec x also becomes 1. So this highlighted portion is the graph of cosec x. On a similar note, the other branches of the same graph can be traced, and by observation we can say that the domain of this function would be all real values excluding what? Where sine is 0, that is the multiples of pi. So you have to include all the multiples of pi where m belongs to the set of integers. Range of the function is going to be all the values till plus from infinity to plus 1, then from minus 1 to negative infinity. That is all real numbers excluding the interval minus 1 to 1. So it will be a set of all real values excluding what? Minus 1 to 1. But as we can see, minus 1 and 1 are included in the range, so we don't have to exclude them. And as we can see, the period is going to be same as sin x, that is going to be 2 pi, because the graph repeats itself after an interval of 2 pi. Let's move forward. Now we are going to discuss the greatest integer function. Now let's look at this term and try to figure out what could it mean. Greatest integer function. So if I say what is the greatest number till the number 5, I'm saying x is equal to 5. Now what is the greatest number till 5? It could be 4.9, it could be 4.99, it could be 4.99999 and so on. So we cannot actually say that this is the greatest number. The greatest number just less than 5 does not exist. Therefore we are going to specify that we are talking about an integer. I hope we covered this portion in the previous video, and now we are focusing at just the integer part. If I'm saying the greatest integer till a number, then we have to look at the number which is on the left side of the number we are talking about. To visualize what I just said, let's look at the number line. If I say I have a number 5.5, now I have to figure out the greatest integer up till this function. Then the greatest integer on this number line before this number is 5, and the integer after this number will be 6. So if I'm talking about this number, then the greatest integer, that is the integer on the left hand side of this number, is 5. So the greatest integer of 5.5 will be written as 5. If I'm talking about another number which is 0.1, now on the number line if we look, 0, and here I am going to have 0.1. So the greatest integer on the left hand side of 0.1 is going to be 0. Now comes the interesting part, that is with negative numbers. If on the number line I have a number minus 2.3, now I have to calculate the greatest integer function of this one. So if I have to calculate the greatest integer function of this one, let's draw the number line 0, minus 1, minus 2, minus 3, as we discussed earlier. Now the greatest integer is the integer which is on the left hand side of this number. We have to calculate the GIF, greatest integer function of minus 2.3. So what is the integer which is on the left hand side of this? It is minus 3, not minus 2. When we were talking about positive numbers, if I have a positive number 2.3, then on the left hand side is 2 and on the right hand side is 3. So if I have to calculate the GIF, greatest integer function of 2.3, then the value will be 2. Whereas if I'm talking about minus 2.3, then the number on the left hand side of it is going to be minus 3. Let's take another example to consolidate this point. if the point is minus 8.001, we know 0 is over here, minus 1, minus 2, minus 3, I'm going to have minus 8 over here, then I'm going to have minus 9 over here. So now the greatest integer function when applied on minus 8.001, this indicates to the greatest integer, that is the integer on the left hand side up till this point. So it is going to be minus 9. But in case of this, if it were a positive number, that is to say, if I had to calculate GIF of 8.001, that is this, then I have to look at the number on the left hand side of it. It would have been 8. So the GIF of 8.001 is 8, but the GIF of minus 8.001 is minus 9. So now let's try to sketch the graph of this function. If I have to sketch the graph of greatest integer function, let's just draw the coordinates and then we'll draw the graph as we just discussed. Okay, so when I input any value from 0 to 1, let's look at the another one. Let's look at from 1 to 2. If I'm inputting any value between 1 and 2, not 1 and 2, if I input 1.1, GIF of 1.1 is going to be 1. GIF of 1.2 is going to be 1. If I input GIF of 1.9, this is also going to be 1. This means in between these two, the value is always going to be 1. And what will be the value at 1? If I input any integer at GIF, that is GIF of 8, it is going to be 8 itself, because 8 is in itself is an integer. So if I input 1, I will get 1, and if I input any value up till 2, I am going to get 1 excluding 2. So this is going to be the graph for all the values of x. The output for all the values of x belonging from 1 to 2, the output at y is going to be 1. So it's better to say that GIF of x is equal to 1 if x belongs from 1 to 2, not including 2, including 1. If I'm inputting any value of x that is more than 1, including 1, and less than 2, not including 2, that is excluding 2, then the GIF of all those values is always going to be 1. Now let's look at another point, that is going to be from 2 to 3. If I input 2 inside GIF, because it's an integer, the output is going to be 2. If I input any value between 2 and 3, let's say 2.5, then GIF of 2.5 is going to be 2. GIF of 2.9 is also going to be 2. That means all the values between 2 and 3 are going to give the output as 2, excluding 3, because 3 is going to give us 3. So now as you can see, this is going to be a step function. Between 0 and 1, if I input 0.1, then the GIF of 0.1 is going to be 0. GIF of 0.9 is also going to be 0. That is the number on the greatest integer on the left hand side of these numbers. So the graph in this portion would look like this. Now if you're moving towards the negative part, if I input any number between minus 1 and 0, then the output would be, let's say if I'm inputting minus of 0.5, then the output would be the greatest integer on the left hand side, that is minus 1. And if I input any other number, let's say minus 0.9, this is 9, then also I'm going to get minus 1. So since the output in this interval is going to be minus 1, if I input minus 1, still I'm going to get minus 1. But at 0 I'm not going to get minus 1. At 0 I'm going to get 0. So 0 has to be excluded. Now let's look at the interval between minus 2 and minus 1. If I input minus 2.5, I'm going to get minus 2. For all the values between this interval, I'm going to get minus 2. So the graph would look like this in this case. So these lines, that is the step function, is the graph of greatest integer function.